So 3 minutes, try and label each structure. All these are right here, so it's not too hard. It's okay. It's all right. Nisha, pretty exceptional. What's that? All right, good. It's got 5, so trigonal bipyramidal. Oh, hello.
It's Nisha's magical hair.
About time, Cooper.
What he said, Nisha. That was Derek. But what he said.
Turn your camera on. There we go. Is Derek talking about your hair?
Yes.
Have you thought more about that one thing I texted you, Nisha?
I mean, yeah.
Okay, you've considered it?
Oh, yeah.
Okay. Oh, yeah. That's good to hear. All right, what do we have here?
Whoa, what's going on with Nisha?
Don't worry about it. Isn't it? It's the same as this one, right? All right, good. What about this one? It's still just linear. 1, 2 electron domains. We don't do this one in chemistry. I don't even know what's there. It's this thing. All right, what would we have here? Octa. Do you know where I'm getting these numbers or these things? I'm counting all of them this time, not just the molecular. So these I account for in the molecular geometry. This would account for all of those and the non-bonding pairs.
Is Cooper eating something other than rice?
Are you? Is that a rice bar you're eating, Cooper Lloyd?
Oh, so actually, our great principal, Mrs. Kent, bought us a little fruit bowl.
Oh my laws! You guys.
So we're eating a little fruit bowl in here. But look at this white rice. You guys, can you see it?
I like rice, especially made by a Polynesian.
I don't think this was made by a Polynesian, but
Wasn't it made?
it was made by ours truly, Sophie Burgraff.
Huh? Who is what?
What?
Never mind.
Who is Caucasian?
She?
Oh, she is Polynesian. Oh my gosh, I'm sorry.
Wow, that's weird.
I love rice from Polynesians. I know it's really it's good rice. It really
Yeah,
is.
it's good. It's my fault for knowing more.
So dumb. Oh, funny.
We're good. Hey, how come this one is the same both times? Okay, like all you said probably the same answer, but you said it all at the same time, so I have no idea what you said. But I believe you probably said because all of the bonding, or sorry, all the domains are bonding, or there's no lone pairs of electrons, which is the same thing, just written a different way. So if Candy Graham, all right, come on in. All right, well, it is pretty impressive hair, but I'll teach. Hey, right here, look at this. Look at this. 30 seconds, go.
Hey, Nisha and Caitlin, let's discuss.
Okay, go ahead.
All right, Cooper, what do you think?
Hey. Okay, so I actually think that it's C.
Those ones should all be bonded, shouldn't they?
Because I have a 1 out of 5 chance of
Actually,
getting it
those
right.
ones should have an unpaired
Yeah.
to finish the end.
So Cooper, do you think
Yeah.
you can H3?
So actually, just explain it to me for real.
I can't hear Cooper.
Hey guys,
Okay, that's what we think too.
you think it is that too?
Yeah.
Okay, cool. That's exactly what I thought.
That was your moment, Coop. You rocked
Can you believe I
that.
got that?
Okay, here we go. 1 sec, I'm gonna mute you. All right. If you can't, listen please. If you can't reason through it, then you should draw it out. I won't spend the time to draw it out, but the answer is C.
Okay, good. I'm so glad I came up with that.
And
See, I was telling you I was right.
yeah, and NH3. Look, if all else fails, you could guess it was the one that had 3 things attached, because that would give you 3 that are bonding. That's 6. That would leave you with 1 pair non-bonding. Now, that doesn't always work, but all else fails, go for it. A diatomic molecule would never be one of these unless like we had different diatomic molecules, but the ones we have, negative. All right, so both of those are out. Cl4, well, it's got 4, so it doesn't have any non-bonding. Hydrogen can't, it only shares 1 pair. So any bond here, you'd have H, O, O, H, and you'd have right here. And then you'd have these, and you'd be there. So there's plenty of unbonded. So if you can't reason it through in your head, then draw them out. All right, here we go. Okay, so let's talk about how to find the molecular geometry of a large molecule. And the answer is you just chop it into its parts. You do 1 central atom at a time. So we would just take that one, and it's not too hard now. Ignore all that. We would just count up the electron domains. 1, 2, 3, 4. So tetrahedral, bond angle, 109.5. That would be that one. Then you would move to the next central atom. And you would look here. It's a little big, but I think you get the idea. Okay, whatever. C has 3 electron domains. So tell your partner 3 electron domains where none of them are non-bonding. What would we call that part? Good. You guys can either A, know the answer, or read. It's trigonal planar, right? And then we move to the last one. Is that my son? Hello, Derek Davidson.
It is your son.
Is he happy or is he grumpy?
He's really grumpy.
Somewhere in between.
You're between.
He doesn't even want to talk to me anymore. It's crazy.
Oh, that's like me. It's what happens with teenagers. All right. So O now it has 4 electron domains, but 2 of them are non-bonding, right? So its electron domain geometry has 4. So we have tetrahedral, 109.5. So we would be able to do this. If we were required to draw it, we could look at it. We would have tetrahedral, trigonal planar, and bent. You do like it or don't like it? Why? Well, you just break it apart and draw each one individual. It really is not that bad, I promise.
So how is the OH bent if there's 2 non-bonding? Oh, they're above.
They're right here, pushing down, just like water. So this is water, sort of, except for this would be the other H. Yes, Reese. Okay. So when you are asked for the geometry of a large molecule, you would name it for each of the central atoms. Okay, a central atom means it's not one hanging out on the edges. So there are 3 central atoms. Probably not. It could. It could. Usually, and I have one on my test. So go ahead.
So, is there a way to figure out like what the angles are, or are we gonna
You can think through most of them because it's just dividing a circle into coordinates. So a circle is 360 degrees. So like trigonal, you just divide it by 3. It's 120. 4, it's 109.5. Not 109.5. It's because then you have the up one. It is 109.5. So not, I don't know, a lot of them, it works this way. The other ones you just got to memorize. So it's in the chart on page 330, whatever.
It can either be 90, 109.5, 120, or
And then there's a 107 for a double band, but you don't need to super memorize them. All right, so this is how it would look on the test. It would ask you to draw the Lewis structure for C3H8. I'm not going to put the H's, but on the end of each tail is an H. You okay with that? Now, this is a bigger chart, so you have to do more. This is just part of it. All right, so then it says geometry of the central carbon atom. Now, a lot of kids get confused. They're like, well, which one? Well, if it says the central one, it means that one. So we would look and say, all right, it has 4 electron domains. These are H's, so all of them are. So we'd say it is tetra. Now, we don't know how to do this yet. We don't know how to do that yet. Okay, it'll look something like that. We'll come back and do another practice one just like this. Okay. Oh, by the way, then it would have the math that we did. We won't work on that today, but we'll talk about it again tomorrow. All right. So this is the next step. If you're putting like a divisor in your notes, we're beyond the VSEPR, and we're now on its application to the polarity of substances. All right, in chapter 8, we discussed bond dipoles. Bond dipoles were when a more electronegative atom pulled electrons towards it. You okay with that? So we'd say, hey, this bond is a polar bond. This bond is a polar bond. But we're going to learn that together, since they pull directly opposite of each other, that the molecule itself is non-polar. So the polarity of a substance depends on the atoms involved and the structure. Go ahead, Gabe. Yeah, you can look at it that way. So we'll talk a little bit today about these arrows. And if you would think about them as what we call vectors in physics. In physics, if you have 2 vectors and you want to add them, you take and draw the arrow, and you would do it on graph paper so you were exact. You would draw one vector going this way. That's what this represents. And then you take the other vector and you put the tail of it on the head of the other, and then you draw the exact direction. So you would put the tail of it here and draw the head of the other. And then if I originally moved that way and then I moved back this way, where did I really move? Nowhere. If our vectors cancel out, we have a nonpolar substance.
So this only works if they're exactly the same.
Yep, sort of. If they're symmetrical, they're going to cancel out. Did you ask an actual question? Sorry. Start the very first part again.
Is the dipole moment just when there's like 2 polar bonds that cancel?
Okay, no, sorry. We would say that this thing would have 2 dipole moments, but together they cancel each other out. So it's kind of weird. We want to know that, hey, oxygen definitely and carbon have a polar relationship, but together in the bond, they would cancel each other out. It's like I walked 5 feet forward and walked 5 feet backwards. I really don't go anywhere. All right. So just because a molecule possesses polar bonds does not mean the molecule as a whole will be polar. So here we go. By adding the individual bond dipoles, one can determine the overall dipole moment of the molecule. So this is another vector thing for water. All right. We have water where oxygen, there's a dipole moment this way and a dipole moment this way. So what we do, that's a handsome man right there. Once again, vector-wise, we would put one arrow, and then we put the tail of one on the head of the other, and then we would draw what's called the resultant vector, and it would say that the electron's overall movement is straight up. So that leaves this side positive, this side negative. So we'd say water is polar for two reasons. The OHs have a dipole moment, and since the structure is a bent structure, we will have both polar bonds and a polar molecule. Red is showing high probability of finding electron. Red is showing low probability. All right. Wow, did I really spend a day last year between those slides? That's ridiculous. Okay, so here we go. Let's discuss, why would this be polar? That's because there is a dipole moment here, and there's nothing to cancel it out. If it was possible to have another Cl over here, then they'd cancel each other out, but it's not possible. Okay, now we have CCl4, and this one's really tricky. They'll use this example a lot, but they'll like throw an H right here. And you look at it, you're like, oh, I know this is nonpolar. I learned this. Yes, big brain. I feel awesome. Can we only test on this? But they've screwed with your mind. They switched something up. So always double check both the structure and the molecule. But yes, since there's a dipole moment that way and that way and that way, if I added all of the resulting vectors, they would be canceled out by the one that's going straight up. So since this is symmetrical and the same type of bonds, it's nonpolar. Nonpolar. This one's polar. Think about that. Remember, there's an electron pair that squished these down. All right. But there is a dipole moment moving this way, and this way. So why is it polar? It's nonpolar because if we do the vector analysis here, I have one this way, and then I take the other one, this one, and I put it this way. And then I take this one and I put it here, and the electron really didn't move anywhere. It's being pulled equally, so it doesn't really move anywhere. Okay, then this was the warning, like I said. This is tetrahedral. It seems pretty symmetrical, but we have chlorine that kind of ruins everything. So you end up with an overall flow or dipole moment up. What's that? Yeah, not this year. You want to be negative in 2020. Then you're not positive. It's a Rona joke.
Wow,
Okay.
Davidson.
I thought it was.
I completely understood that. Can that be the only thing on the test?
Yes. Everybody. Fabian has a large brain. Large brain. Large brain. All right. So if I come back here.
There's a difference.
What?
It's just a thick skull. There's a difference.
Okay. If we come back here, just quick. Find 3 that are polar and 3 that are nonpolar. 3 polar, 3 nonpolar.
I got 3 non-polar, and I got
All right, here we go. I'm going to go quick. Nonpolar, right? Polar, nonpolar, nonpolar. It's symmetrical. Notice, well, I'll wait for that. What do we got? What do we have here? Y. This one's polar.
Because there's a fifth S, that's something.
So we have 1, 2, 3, 4.
It's missing another
It's
four.
it's square pyramidal, right? I'd actually have to check. They might cancel out, honestly. I've changed my mind. I do think it's nonpolar now that I think about it. Because it has the wedges.
Yeah, but if you think about it three-dimensional, it's going up, and these things are pulling out. These aren't pulling down.
Okay, I'm pretty sure it's nonpolar.
I think it's not polar.
'Cause we're gonna have the F that points straight up, right? Each one of these pulls slightly away and down. That had the wedges. All right. So all of them will cancel the side to side out. All 4 of them with their slight downs will have an arrow that will pull this one down. So it is nonpolar. Well, probably not. I usually stick with standard things that we're kind of used to, like water and sulfur dioxide and ammonia. All right, what do we have here? Nonpolar. What do we have here? Nonpolar, polar, polar. This one's tricky. It would be nonpolar except for we switch up the element, right? All right, so if we really get really down to it, if I remember, these might even be the same, 3.5 and 3.5. So it technically might be nonpolar, but for now, if it switches anything up, call it polar. How about this one? Nonpolar, polar. If you get that wrong, you're kicked out of AP chemistry and you fail biology from last year. All right. Nonpolar, nonpolar, polar, polar. We all right with that? Okay. Coming back. All right. This is not bad, but some kids, I don't know why they don't, whatever. So it sounds tricky, but it's really easy in the end. We think of covalent bonding forming through the sharing of valence electron by adjacent atoms. In such an approach, this can only occur when orbitals of the 2 atoms overlap. So it turns out we have a few ways to overlap. We can have s orbitals overlap. So that'd be like one square with one and another square with the other. Okay, that would be s overlap. And we can have an s and a p overlap. So your s's would be full in the one, and it'd look like this. Okay, and then I'll put it in red. We'd have an s block twice. So like this is representing H2O. And in this type of relationship, we have the overlap of P clouds and S clouds. All right. And then sometimes we'll have it where the P clouds overlap, like chlorine to chlorine. All right. So if it was chlorine to chlorine, it would just be like this, these 2 boxes overlapping. So there's 3 ways we have overlapping bonds. These are going to have different names. Well, they're coming up actually. So once you know the electron domain geometry, you know what we call the hybridization state of the atom. And hybridization is the way we describe this mixing of your s and p orbitals. So the way it works, and like it's complicated, but the test and answering it is really simple. When we find the electron domain geometry, so we have linear, we have 180, it has 2 lobes, 1, 2. So we're going to say that requires 2 things. We start with an S, and I know this is kind of tricky. S could always hold 2 before, right? But now we're talking about sharing. So the maximum that S can have is 1 shared pair. Here we have 2 shared pairs. So that requires an S and a p orbital in order for that to happen. If we now have trigonoplanar, we have 3 things. That requires an S. We always share S first, and then 2 p's. If we add the numbers up top, it will always add to the number of electron domains. If we have tetrahedral, we have 4. 4 requires an S and 3 P's. So once again, I know that it used to be S2P6, but we're sharing now, so we can make 1 pair and 3 pairs. So the maximum numbers up here are 1 and 3. So in order to get above that, if we have 1, 2, 3, 4, 5, we now have an S, 3 P's, and 1 D, and 6 SP3D2. So what's that? It's like it's complicated science, but it's easy testing material. We should only do this. You count the electron domains, and then you make sure your S, P's, and D's add up to that number. So if I come here, way back, oh, it's not that far, it's right here again. So let's come here. I have 1, 2, 3 domains. So that would mean it is S, which max is 1, and so P, I need how many more? 2. How about here? It counts these 2. All right, and then we have SP 3. So you find the electron domains and assign SP. If you need, you can go to D, and their max value is half of what it used to be able to be. I will review that tomorrow. I know you're like, what is he talking about? But we'll live. All right, so let's talk about the last thing. This is valence bond theory. All right, are we out of here in 20 seconds? Or 5 more minutes? Okay, oh, 10 more minutes. Wow, what a great day to be alive. Okay, the last piece of all of chapter 9 are what we call sigma or pi bonds. Pi bonds are on the next one, I think, yeah. So as these things come to overlap, we have 2 ways that they can overlap. End to end, and I'll come back, so don't worry, end to end or side to side. You okay with that? That's 2 ways that they can overlap. The first one, side to side, I like to compare it to a fist bump. All right, the circles come to the side and they just overlap a little bit. All right, so sigma bonds are characterized by head-to-head overlap. Look how content he looks. Oh, now he's looking away. Hi, Cooper.
Hey, Davidson.
How much money we made today?
I think, what are we at?
Today, not
1,800.
much.
So not actually a ton. Well, I think we made like $600.
That's still pretty good.
It's still pretty good. So I think we're up to like 1,800 right now.
Gotcha.
We only need 200 more to take away our phones. So
Not yet.
if anyone wants to take away our phones, now is your time to do it.
All right. I'll send a check down. That's a good question. All right. Pi bonds are characterized by side to side overlap. So that's more like a handshake. I don't want to know. So handshakes, much more interactive interaction, right? Yes, that's why we elbow bump. No, I don't want to hear. Yes, oxygen would have both. We'll see why here in a second. All right. This is the most important part of sigma and pi for you. And it's the only thing that's ever tested about valence orbital theory. And that is the fact that single bonds are always sigma bonds because sigma overlap is greater, resulting in stronger bond and more energy lowering.
So as long as it's not a double sigma,
Yep.
if it's double, can it be a sigma?
it's a sigma and a pi, which is, it's going to say this. You'll see. In a multiple bond, one of the bonds is a sigma bond and the other, and sorry, the rest are pi bonds. Hold on, let me see what it says. Okay, do you need that? I'll summarize here in a second. All right. So, to summarize, a single bond is always a sigma bond. A double bond is always a sigma and a pi bond. A triple bond is always a sigma and two pi bonds. So how many sigma and how many pi in C3H6? So this is how you'll have to do this on the test. You'll draw this. So it's C3H6, which when you draw it out, it's going to require one double bond. This structure, by the way, it doesn't matter if the H goes up or down on the middle one. It doesn't matter. So we would look and you count up every single bond. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 sigma bonds. And the second thing you do is you count up any double bonds. 1 double bond. So that's your pi. And there's your answer. How many sigma? There's 8 of them. How many pi? There's 1 of them.
So you still count the double bond as a single bond as well?
Yep.
Okay.
That doesn't seem too awful, right? So remember that chart a while ago I showed? We can now fill in the rest of the answers. I'm going to go back. Does anyone need more time on this slide? Okay, where are you? Right here. Okay, so we want to know the hybridization of the central carbon atom. So I know it's tetrahedral, which means 4, right? So hybridization, I'd put sp3 because there's 1 s, 3 p's, that adds to 4. All right, number of sigma bonds in the molecule, I count every bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of pi bonds, I count how many double bonds there are. Are there any? There's 0. And that would be a third of that multiple choice test, or fill in the blank part. Yes, Judah. Yeah, like a triple, you mean? Okay, so yes, if this was a triple, we would count it. So pretend it's a triple for a second. So you'd count every bond still. 1, 2, 3, 4, 5, 6, 7. So you'd have 7. And then you would count this one 2 times. Is that fair? Good. Each second, third, or fourth bond is your pi bond. Okay, I feel like that's good. We'll review tomorrow and